This lesson will cover horizontal transformations. The learning goal is to explore the effect of horizontal stretches, compressions, and reflections on the equation of a function and its graph. If there are success criteria, you can describe the transformations of a function based on its equation or graph, and you can create the graph of a transform function. So we know for the general equation, a of f times k x minus t plus c, the variable k represents the horizontal transformation. Now this is the horizontal stretch, compression, as well as reflection. Now once again, there are several ways of graphing function transformations. Most will use the parent function shape or points to determine the points of the transform function. Now we're going to be graphing functions of the form f of kx, where k is greater than 1, but where it's between 0 and 1, and where it is negative, which should be k. Now the thing to note here is we are a bit familiar with how this works when we were graphing quadratics last year, is that horizontal transformations actually do the opposite of what they seem to be doing. So while we were looking at vertical stretch expressions and reflections in the previous lesson, where they did exactly as you would expect. If a was a value greater than 1, it would multiply the y value. It's the opposite for k. So let's first graph our base or parent function for root of x. So let's get root of x here. So here we have x, here we have y equals root of x. Get our key points 0, 1, and 4. And for y, that's 0, 1, and 2. And here we have k equals 2. So this is a horizontal. It's completely out of whack there. See if I can get that back. There. So this value, this 2 right here, let's keep that far away. That is a horizontal compression. Would you say, okay, wait a minute, that value is multiplying the x value by 2. Oh, I need these values back. But this is how we want to look at it. So let's say we had our old x value here. So our old x value, it's going to be mapped onto our new x value, which is 2 times the new x value. But we need to actually get the new x value from this. So we would divide, I should keep that over here, we would divide that side by 2, cancel these, and that would tell us that our new x value is actually the old x value divided by 2. It's a way of looking at it. If you look at this in terms of various graphs, you'll see the pattern where anytime you do horizontal transformation, is the opposite of what it appears. So opposites for stretch and compressions, so reflections stay the same because it's negative, but translations will also have that opposite effect. So our new function here, or let's plot our parent function first. Let's change colors and let's do our transform function. So our new table values for transfer function, y stays the same. There's no effect on the y values, so we 0, 1, and 2. And for our x values here, our new x values are half of the previous x values. So we're taking each of these and we're dividing them by 2, or we're taking half of them. Half of 0 is 0, half of 1 is 1 half, half of 4 is 2. So these become our new coordinates. So we have 0, 0 stays the same. We have 1 half and 1, so that's about right here. And we have 2, 2. So we're taking our function and we're compressing it horizontally. So when k is greater than 1, when you have a whole number in front of your x value, it's going to be when you have a number greater than 1, it's going to be a horizontal compression. If k is a decimal or fraction between 0 and 1, it's going to be a stretch. Horizontal stretch, so it does the opposite. So here we have x squared. Let's get our parent function on here. Let's get a table of values, so negative 2, negative 1, 0, negative 1, oh, positive 1 and 2, and we have 4, 1, 0, 1, 4, x and y equals x squared. And then our transform function is here. We have half of x, so we need to do the opposite of that. So we want to do 2 times of x, and then y is the same. Y remains as 4, 1, 0, 1, and 4. And here we're going to take each of our x values and we're going to multiply each of them by 2. So that gives us negative 2. Oops, gives us negative 4, sorry. Negative 4, negative 2, 0, 2, and 4. So multiplying each of our x values here by 2. We can now plot these points. So we have negative 4, 4. We have 2, 1, or say negative 2, 1, 0, 0, 2, 1, and 4, positive 4. So this is a horizontal stretch. We're opening up this graph. So again, for horizontal transformations for the k value, it does the opposite of what you see. If it's 2x, if it's multiplying by 2, you're actually going to be dividing by 2. If it's multiplying by half, or here, if you're dividing by half, technically it's divided by 2, you're going to be multiplying by 2 instead. So you're doing the opposite of what the transformation, what you think the transformation would be. So think of it as the opposite of the vertical transformation. And then finally, if k is less than 0, it's going to be negative. We can take this function up here. We have the same parent function. So we have root of x key points is 0, 1, and 4. Y values is 0, 1, and 2. And we want our transform function here. So here, let's do blue. Change colors. Our y values again stay the same. There's no effect on them. But our x values, if it's k is negative 2, then we need the opposite of that. So that is negative a half. So it's negative 1/2 of x. Taking these x values and multiplying all by a half, or dividing them all by 2, or negative 2. So that's 0, because 0 is unaffected here. That's negative 1/2. 1 times negative a half is still negative half. And 4 times negative half, that's negative 2. And we can plot these points on our graph. We have negative half and 1, and negative 2 and 2. A compression and a reflection. So in summary, the k value function is a horizontal transformation. These should all say A, not K. Let's change those quickly. So if k is negative, you're reflected on the y-axis. Oof, there's a lot of things that change here. Reflected on the y-axis. If k is greater than 1, then the graph is horizontally compressed. And if k is between 0 and 1, the graph is horizontally stretched. So again, given any function, we can apply a horizontal transformation to it. So using a similar function we have from before, we're going to sketch f of negative a half of x. We have to look at this, and it's negative a half. This is horizontal, so it does the opposite here. So where you might think, this is a compression, it's actually a stretch of 2. It's a stretch by a factor of 2. So here, this is a reflection on the y-axis. It's negative. And it's a horizontal stretch by a factor 2. So we're going to take each of our coordinates here, and we can multiply the x values by negative 2, or we can plot them once at a time, so we can reflect them and then multiply them by 2. Either or works. So here I have negative 3, so multiplied by negative 2 is positive 6. That'd be way over here. This x value is -2, so multiplied by -2 is +4. So +4 is about right here. And then we have this point right here. This is on the y-axis. It's not going to change position because it's x value is 0, and x or 0 multiplied by anything is just 0, so it just stays where it is. This one, x value is 1 multiplied by -2 is -2, so that goes right here. And then here our x value is -3 multiplied by -2 is -6, so that's way over here. We can connect the points. So when given a function, just look at the coordinates themselves and apply the transformations to those coordinates.